Hi, Cedarville University students. This is our virtual lesson today. Before we get started, I do want to remind you that during our lesson today, there's going to be a lot of opportunities for you to stop and watch some YouTube videos. I will have those linked in the description below. So if you would check those things out, you might want to pause this video, then open those up. Also, I do want to remind you that there is a test coming up. It is 1 week from today. So that'd be October, I don't know, but it's on Tuesday. I forget what the date is, but there's a test coming up. So I just want you to be prepared for that. Also, I have made a Kahoot for you guys to work on, and I would appreciate it if you do that review Kahoot, and that is linked in our Canvas classroom under the electricity module. So if you would please check that out. I'd really appreciate that. So, and there's some content in there that I want you to visit. So, let's go ahead and get started with electricity. And this is kind of our last section in this trimester. Once we're done with electricity, we take our test and then we move on to our very last trimester of class. So let's go ahead and get started. So here's electricity and a blank slide. And I just thought this would be kind of fun. This is something I found on the floor of my classroom a few years ago, and I just thought this was kind of interesting. Mr. Wagner looks like a potato and a unicorn poppy dopey face. Listen, our kids sometimes struggle to be mean, and that's just, if that's the meanest they can work up, we got a pretty good crew of kids. So you'll see fun things like that, and you'll just want to share them with other people. And some of these pictures, these are from a while ago. Here's Elsie just chewing on her periodic table blocks, and Elsie on a little horse at a fall festival. I think that was last year. And here's a picture of our family from last year on a fall hike. This last weekend we went camping. I'll have to show you some of those pictures in a little bit. And there's our girls on a fall hike as well. But anyway, let's go on to some science. First thing we need to talk about is we need to talk about atoms. Before you can understand electricity, you need to understand atoms. And our next trimester is going to have a lot of information about atoms and things like that. But some basics. Atoms contain protons, neutrons, and electrons. The protons have a positive charge, and they're stuck inside the atom. They cannot go anywhere. They cannot move from place to place. The electrons, however, they can move from place to place. They can be shared. You probably remember that from chemistry class. If you look at the atom here in the picture, this drawing, it says that there are 3 protons, which are positive charge, and there are 3 electrons, which are negatively charged, making this an overall neutral atom. But not all atoms are neutral. Some atoms are ions. An ion is an atom that is not neutral. So it says right here, electricity occurs from the differences in charges. So let's go to our next slide. And if at any time you do need to pause while you're taking notes or anything like that, feel free to do so. Ions are atoms that have an overall negative or positive charge. If you look at the atom right up top here, we've got 2 protons. Those are the red things right here. And we've got 3 electrons. Well, 2 positives, 3 negatives. That means this atom is an ion. It's a negative ion because it has an overall negative charge. So some atoms can be ions. And ions are necessary in things like batteries. So here I've got a negative ion because it's got a lot of electrons. Here's a positive ion because it doesn't have as many electrons. It says ions are atoms that have an overall positive or negative charge, and ions can move through a solid. Cannot move through a solid, but they are free to move through a liquid, which is why most batteries, like this battery down here, is a liquid, because the ions are able to move from place to place. It doesn't work so well in a solid. So it's this differential in charges. It's what creates the positive and the negative side on a battery. It's the ions. But that's how batteries work, and batteries create their own form of electricity, direct current, and we're not going to spend much time on that. It says the ability for ions to move in a liquid is what allows batteries to work. I just told you that. So let's keep going. Protons and neutrons are fixed in the nucleus. I'm sorry, I'm hiding the nucleus. So remember, we said that these are the electrons on the outside. And then we're going to say that these red ones right here are protons. It's a positive charge. We've got 3 protons, 3 electrons. This is not an ion because it's overall neutral. It doesn't have a positive charge or a negative charge. However, electrons are able to move from place to place. It's the moving electrons is what creates electricity. And that is the foundation for everything that we're going to learn about electricity, is that the electrons can move from place to place. Let's keep on going. So, insulators and conductors. Insulators are materials that do not allow electrons to move easily from place to place. Some examples of insulators would be things like rubber, plastic, wood, or skin. All those things are insulators. They do not allow electricity to move through them very easily. However, things that are conductors that can move easily from place to place, those would be things like copper, aluminum, and not just pure water. It's water that's going to have ions in it. So that would allow electrons to move easily from place to place. Some other things that allow electricity to move from place to place, you can find in the videos that I'm going to link down below. One is a fear factor from a Tesla coil, and someone is wearing a chainmail suit, kind of like what old medieval knights would wear, and they're getting electrocuted with all these different volts of electricity. First of all, it's not the volts that are going to hurt you, it's going to be the amps, but that's later on. And you might say, how is this person not getting electrocuted? Well, the electricity always takes the path of least resistance. And in this case, the person is wearing metal on their outside. That's the conductor. Your skin is an insulator. So the electricity is actually flowing outside of his body in the fear factor Tesla coil. If he was not wearing that chainmail suit, there would be a very much different story. And I certainly wouldn't show that to you on a video. And then there's the next video. You don't have to watch the entire thing. It's just there for you to kind of help you out. It's not critical to the learning process, but it's Architect. They actually use a Tesla coil, and it vibrates at a certain frequency in order to make music. It's not critical for you to learn, but it's still kind of fun. You don't have to watch the whole thing. Maybe just watch the first 20 seconds. So here's a copper wire. Great conductor. Let's keep moving on. Now let's talk about electric force. When it comes to electric force, we've got electric charges, remember? And if we have opposites here, we've got a positive and a negative. Opposites attract. Here we've got a positive and a positive, or a negative and a negative, and like charges repel. So it says a force is a push or a pull caused by electric charges. And electric force is the attraction or repulsion of like and unlike charges for each other. And that reminds me, this is way back in the early 90s. Paula Abdul, she sang this song with this cartoon character, and the song is called Opposites Attract. I'm pretty sure it was all about electricity. People tell me it's not, but I'm going to say it's all about electricity. And it's just kind of a fun song, but I'm not going to even link that down there. But Opposites Attract. It's a song, it's science, it makes sense. Keep that in mind. You'll need to know that in a little bit. So let's talk a little bit more about electric force. Here, notice we've got the positive and the negative. They got hearts because they're in love. And over here, we've got a positive and negative. They're in love because opposites attract. But look here, negative and negative, they repel each other. Positive and positive, they repel each other. But look what's going on right here with this comb. This comb is picking up this tissue paper. What do we know about the charges of the tissue paper and the charges of the comb if they're attracted to each other? We know that they are opposite charges. And here's another example. Take a look. We've got a cloud here. We've got positive up top, negative down at the bottom, and you're probably thinking, I didn't think protons could move. You're right, they can't. The entire atom in this case moves. And we've got all sorts of negative ions down here. And we've got an electric charge down here and a positive charge right here. And they're attracted to each other, and they can only equalize through lightning. So there's a demonstration I want to show you guys that is linked in the video down below. And it is of me demonstrating a Van de Graaff generator. Granted, I have a much, much smaller Van de Graaff generator than in this picture. And a few other things about opposites attracting and like charges repelling. So there would be a demo with balloons, which I didn't link in there. I didn't have time to do that. And the demonstration that I really encourage you to watch describes the electric charges, like in someone's hair. And it's asking, why is the girl's hair separating? And that's discussed in the video. So if you wouldn't mind pausing this video right now to watch that video that's linked down below. And it's of me doing a few demonstrations. Okay, so let's move on to our next slide. And the next thing we need to talk about is an electric field. Think of electric field a little bit like magnets. When you have a magnet, around the magnet there is a magnetic field. Same thing with planet Earth. Planet Earth is magnetic, and there's a magnetic field around planet Earth. Well, it's the same thing with electricity. You don't physically have to touch electricity in order to become electrocuted. You just have to get close enough to the electric field. So an electric field is an area around an electric force where a charge can be felt. Hey, that has a lot to do with light, doesn't it? Because a moving electric field creates magnetism, and a moving magnetic field creates electricity. Well, if you look at this picture down below here, they've got clamps on these multimeters. And as the electricity is flowing through, it makes a magnetic field. And you can measure that magnetic field with one of these little clamps, these multimeters, and it's going to tell you how much electricity is flowing. And it says the electric field gets stronger as you get closer to the source of the electric force. So think of something that's like power lines. They have a lot of electricity flowing through them. So the closer you get, the more likely it is for you to feel the electric field around there. This particular video, I don't want you to watch the whole thing because it's not entirely necessary, but there's a part in this video where someone takes light bulbs, just the long skinny tube light bulbs, and they jam them in the ground underneath power lines. They are not touching the power lines, they're just close to the power lines. And since they're close to the power lines, they are within the electric field. And that is enough electricity to light up those light bulbs that are not touching any source of electricity. You just have to be close enough. Kind of like a magnetic field, there is an electric field, an area where the electric force can be felt. And let's talk about induced charges next. So an induced charge is a charge when an object creates an electric charge in another object by way of an electric field. That sounds really complicated. Let's break it down. If we look over here, we've got this ball. Let's call it a balloon or something like that. And we've got this wall right here. Okay, and we're going to say this wall is a conductor. Maybe it's a metal or something like that. I'm not entirely sure. But this ball is overall negative. And you bring the ball that's overall negative, you bring it very, very close to this metal wall or this metal pole or whatever it is you want to call it. What happens to the electrons in this metal rod? Remember, the electrons can move. The protons can't. So if you bring this negative charge over here, negative and negative repel. Look what happens to all these little electrons. They fly away. They move elsewhere because they're repulsed by this negative ball, leaving this space right here in our metal wall overall positive. Now, are the two physically touching? They're not. They're just very close. That's called an induced charge. And it's just because they're very, very close to each other. It's what creates the charge. They don't have to physically touch. There's a video of a floating bag. And we tried this one winter at my house, and my daughter thought it was fun, and she was recording. And I had a PVC pipe and a rabbit pelt, and I charged the PVC pipe, and then the bag floated a little bit. You don't have to watch the whole thing, maybe just 5 or 10 seconds, and you'll get the main idea. But it's a good example of an induced charge. Also, there's going to be an MIT electrostatics demo down below. I apologize, there's going to be a lot of videos that go along with this. And he talks a little bit about induced charges there. So I do highly recommend watching that one in its entirety. And I think that one will help your understanding. Another way to describe it, take a look. It's a very similar situation that I just described. We've got a balloon with a negative side. Someone rubbed it on their hair and they have electrons on it. So this balloon's got a negative side. What happens to all the electrons in the wall? Well, negatives and negatives, they repel. Can the positives move away? No, they wouldn't want to, because they're attracted to the negatives. So can walls normally become charged? No, walls aren't normally charged. But since you put this negative balloon next to it, now we've induced a charge. We've made a charge. That's called an induced charge. So a negatively charged balloon causes the electrons in the wall to move away, and that is an induced charge. So why didn't the positive charges move? Great question. Because protons cannot move. They're not able to. The electrons are the things that are able to move. And there's a little interactive demo that goes along with this. And I know when I click this, this is going to change things up a little bit. So let's see if I can't shrink the screen just a skosh and get this available for you guys to see. And I don't even know if this is going to work. Let's give it a try. All right, I think we're just waiting for this to load. I'll pause my video while we wait for this to load. I'll be right back. Okay, I'm back. All right, hopefully this will start working. It seems like my video is stuck. There we go. All right, so I got to put myself over here, and let's demonstrate an induced charge. So we've got this balloon right here. Everything's hunky-dory and everything's neutral. We've got protons and electrons, and everything's equal right now. There's no charges on anything. But we're going to take our balloon here, and we're going to rub it on the sweater. And when we rub it on the sweater, take a look. We built up a huge negative charge on the balloon. Why? Because balloons are not conductors. They're insulators. So they hold on to the charge. See, look at this. Our balloon, it's overall negative. Our sweater is overall positive. They're attracted to each other. So I let go. But let's take this balloon, let's take it over to the wall, and let's see what happens to the wall when I bring it over here. Whoa, look what's happening to all the electrons. The electrons are moving away, which creates the wall to be overall positive. Do walls, are they normally positive? They are not. Instead, we have induced a charge. So all we did was bring something negative very close to it, and we've made that overall positive. The same thing can happen in nature. A tree can become overall positive. How can a tree become overall positive? Stick something negative next to it, like a thunderstorm. This thunderstorm's got this negative cloud, pushes electrons down the tree, and then you have an overall positive tree. And then the thunderstorm's like, well, I'll pass some of my electrons onto that, and boom, you've got lightning. So hopefully this helped you understand induced charges a little bit. Plus, it's kind of fun. If you want to try this on your own, you'd go to FET, Colorado, and try a few things like that. Anyway, let's move this out of the way and go back to our PowerPoint. This is just kind of fun. It's something called St. Elmos Fire. And it's because of induced charges, and this is induced charges in nature. Induced charges sometimes occur when large negatively charged storms cause other things to be negatively charged. So take a look at these ladies. There's a storm probably nearby, and it's creating these charges in these ladies' hair. They don't realize that they're actually in quite a bit of danger right there for lightning. But they can feel the induced charge of the storm coming nearby. And this actually happened a lot on old sailing ships, that it would make kind of like little sparks at the very end of their sailing ship, and that's an induced charge from a thunderstorm. And I don't know why, I just thought this was kind of funny because it's called St. Elmos Fire, but it has nothing to do with the actual Elmo. And there's a little video that goes along with this. You don't have to watch the entire thing, but it's from the cockpit of an airplane. And as the airplane is flying through a negatively charged storm, there's lightning that's actually climbing up the windshield of the airplane itself, which is really kind of eerie and kind of creepy to think about. But it's been documented, and people have seen lightning go over the airplane. And that is a St. Elmo's Fire. You don't have to watch that. That is not critical to the learning process, but it's just kind of fun. This phenomenon, St. Elmo's Fire. So let's talk about electric discharge. Electric discharge is the rapid movement of excess charge from one object to another. So you can see here that this hand, hold on, I gotta sneeze. Sorry, I had to sneeze. You just can't plan those things. Anyway, it's whenever something has a very built-up charge, like the balloon did, and it passes that built-up charge onto something else. So electric discharge is the rapid movement of excess charge from one object to another. And you can see like these clouds, as they move over the Earth, they become overall negative. And they create an induced charge to things on the Earth. And a tree or a building or a car or something like that, it pushes the electrons out of it. And now that object on Earth becomes overall positive. And the lightning says, hey, I've got all these extra electrons. I'll give you some. Zap. And that is an electric discharge. I've got a compilation of lightning strikes, which is an electric discharge. It's kind of fun to watch. They're close calls with lightning, but there is a swear word, I believe, in one of the parts. So you might want to plug your ears for that. And again, that's one of those videos. It's fun, but it is not critical to the learning process. So if you don't want to watch the whole thing, you don't have to do that. It's just kind of fun for us to see some electric discharge. And now let's go to grounding. It's more than what happens if you misbehave at home as a youngster. It's providing a pathway for excess electrical charge to flow into the Earth. Next to my house, I have something like this, where the electricity comes out of the ground from the power company, and then into a box where they can, there's a little meter that measures how much electricity I'm using. And then I have one of these things that's pounded into the ground right next to it. This is actually 6 feet long, and you might say it doesn't look 6 feet long. It's because 5.5 feet are pounded into the ground. And if forever, for any reason, that there is excess charge in my house, let's just suppose I'm vacuuming, and I don't know, I vacuum over the electric cord and it starts to tear open and there's electricity flowing into the vacuum. What are we going to do with all that extra electricity? Well, a grounding rod is connected to my electrical outlets. That extra electricity goes through some wires in my house, the neutral wires, which you can find right here. And then where do we put that extra charge? We put it in the Earth. Things that are very massive can accept an electric charge. And the Earth is just one of those things. It can accept an electric charge. Lightning hits the Earth and just goes on its merry way. The Earth is fine. It's not a big deal. So that's what grounding is for. And houses like this house right here, they have lightning rods on the top of the house. And it's like saying, all right, lightning, do your best. Lightning hits this lightning rod. It's connected to a wire that goes alongside the house, which would be connected to something like this. It just takes the lightning along those wires down into the ground where the Earth can accept it. And it's not going to make a big deal to the Earth. So the Earth can accept large amounts of excess charge due to its huge mass. And Earth is pretty big. Houses often ground their electrical outlets to metal water pipes. So some houses, they have like copper pipes that come into their house, and even the pipes that go out of their house are copper as well. So they ground to those copper pipes. And if there's extra charge, it goes from those pipes straight into the ground. The only danger with that is it's also in your water as well. And you can get electrocuted from your water. So you got to be kind of careful about that. That's why it's better to have a grounding rod like that, which is what I have at my house. And so why is it a bad idea? Why is it a bad idea to take a bath or a shower during a thunderstorm? Well, think of your metal pipes in the ground. Those metal pipes, if lightning were to strike your house and somehow go into the ground and then reach the metal pipes, technically it could go into your house. My parents always told me, hey, if there's a lightning storm, it's not a good time to take a bath or a shower. And there is a TED Ed video. We're not going to watch it together for the sake of time. I do want you to watch this on your own. This will be helpful. And I do suggest you watch the entire thing, and I'll have that linked in the description below. So please watch that, and we're almost done. Just hang on, we're almost there. Let's talk about electric current. Electric current is the steady continuous flow of electricity. Everything that we've talked about so far is not a steady flow of electricity, but a rapid discharge of electricity. Electricity going from place to place, zoop, all at once. And the big question that a lot of people struggled with, like Nikola Tesla and Thomas Edison, was how can we continue this flow of electricity instead of just one zap? How can we keep it moving? And that is an electric current. An electric current is a steady continuous flow, unlike electric discharge, which is a short burst of energy. Electric current will only flow through a closed electric circuit. So if you don't have an electric circuit, the electricity is not going to flow. Electricity behaves kind of like water in this case. And if your circuit is not closed, the water is going to leak out somewhere. Same thing with electricity. If the circuit is not closed, the electricity cannot flow from place to place. So here, we're saying the battery is kind of like a water pump, and it's sending electricity here to the load, which would be the light bulb, and then back to the pump. Well, if you cut this right here, the water just spills out everywhere and it doesn't work. Same thing with a water pump. So you got to think of electricity a little bit like water, and that helps you out. So we've got this little animated GIF of electricity flowing from the negative to the load right here, and then overall to the positive. And if you were to open the gate right here, the electricity cannot flow. This is like a open circuit and a closed circuit. So what happens to the flow of electricity when the circuit is open? It doesn't flow. So just a little bit more on circuits. We said a circuit is a closed conducting loop. An electric current is only able to flow through a closed system. If the system is not closed, the electricity does not flow. There is a problem with this picture right here. It's saying that the electrons are flowing this way. So silly. The electrons flow from the negative to the load and then are attracted to the positive. Whoever made this little picture here, they did it backwards, but oh well. In this picture down here, this one's correct. We've got all the electrons down here, the negative ions, and they're pushing electrons through this wire all the way to the positive side. We have a closed conducting loop. We have a circuit. So it says, why do electrons flow from the negative terminal to the positive terminal? And this is not a joke. It's because the electrons in this wire are repelled by the negatives. Remember, negatives repel negatives. So you've got the negatives in the wire, you've got negative charges here, and these electrons are like, I hate you, get away. And then they start flowing towards the positive because they love positive. They're in love with positive. So they just continue to flow. And this closed conducting loop would make a circuit. When we return on Thursday, we're going to talk more about circuits. I'm going to show you some circuits. And we're going to talk about just all things with electric flow, and amperage and voltage and resistance and stuff like that. So we'll save that for Thursday. That's all I got for you today. Thank you so much for paying attention and watching. And please do watch those linked videos down below. I'd appreciate that. Have a great day.